Hello everyone, and welcome back. Last time we finished up looking at light and how it reflected off mirrors, concave mirrors, convex mirrors, how they formed images, real, virtual, upright, inverted. Today we're going to start looking at another property of light, and that is, what does light do when it goes from one material into another material? For example, if light is traveling in air and then hits a surface of water and enters into the water, what happens? We'll refer to those different materials as a different medium, or different media, plural for medium. So what happens when light goes from one medium into another medium? Well, something very interesting happens, and I'd like to demonstrate that. I'm going to use a laser that makes a nice straight line. This might be a little bit hard to see with so much light in here, but I'm going to turn the lights down in just a second so we'll be able to see it easier. And I'm going to take that light that is in air, and I'm going to put it into a block of plastic, and we're going to see what happens when the light goes from air into plastic. All right, let's take a look. Here is our laser, and now I'm going to allow that laser to go from air and into this block of plastic. Let's see what happens. Well, what do we notice? Right at the surface of the plastic, the light bends. It does not travel in a straight line. And then, when it comes back out over on this side, it bends again. So, notice, at this surface, right here, when the light goes into the plastic, it bends. We call that refraction. And this section is section 26, which is entitled The Refraction of Light, Lenses, and we'll take a look at lenses next time. But to continue looking at how the light refracts at the surface, I'm going to turn the lights down a little bit more because I want us to see something else as well. With all the lights turned off, we get a little more glare off the plastic, but there's still something very important I want us to see. So let's take the block and the laser and put the laser through again. And we notice that we get refraction at the surface, but I also want you to notice that we also get reflection. That was a little bit hard to see with just some of the lights off. When the laser from here enters the block refracts, the laser refracts. In other words, the light that enters the plastic bends, but it also reflects. So the light refracts and reflects. Most of the light in this case we can see refracts. We can see that the ray inside the block is much brighter than the ray that reflects on the outside, but it does both, reflects and refracts. And you might actually notice that there is a ray inside. When it strikes the back surface, it refracts again a little bit, and we end up with another ray down here. So we have the initial ray reflecting and refracting, then the ray inside the block refracts and comes out, but also reflects, and then that internal ray refracts again over here. So we get a whole series of reflection, refraction, reflection, refraction as the ray travels into the block, passes through the block, reflects inside the block, all sorts of reflection and refraction. Let's take a look at just how the light refracts at the surface of the block. When light goes from one medium into a second medium, and I'll refer to these as medium 1 and medium 2, the light typically bends. It refracts. It does not travel on a straight line, but it bends when it enters the second medium. This line that connects, that's in between medium 1 and medium 2, we'll refer to this as the interface. The interface just means the surface where one material touches or connects to the second material. The amount of refraction we get depends on a very, very important number relating to a medium, and that is called the Index of Refraction. The reason that the light refracts is because typically the light does not travel at the same speed in the two different media. The index of refraction gives us an idea of the the amount that the speed changes, we will define the index of refraction for a material as c. Now what's c? Remember, c is the speed of light in a vacuum, which was, remember, 3.00 times 10 to the 8th meters per second. And then c divided by v, where v is the speed of light in the medium. So v is the speed of light in the medium. Well, you might wonder, why does light slow down? What happens? To be precise, this is actually what we would refer to as the phase velocity of light. Light in between atoms and molecules of the material travels just like it would in a vacuum at c. But you can think of it as each atom and molecule kind of absorbs the light as it comes in and then re-emits it in the same direction. And kind of that absorption and emission slows the light down just a little bit, essentially. And we actually refer to that as the phase velocity. But what's important is the phase velocity is always less than c. In some materials, it might be very close to c. And when that's true, n might be very, very close to 1. But in any other kind of material where it's not close to 1, what we're going to end up with is a value of c that's larger than v, and n will then be larger than 1. Here is a number that I want you to remember. Remember, I already told you, you need to remember the value for c. Another value you need to remember, and in particular I'm talking to the students taking my class, that is the index of refraction for air. And I'll write this as n sub air. The value of the index for air is, and you've got to remember this, 1.00. Well, it's not too hard to remember, I think. It's actually a little bit larger than 1, but to 3 significant figures, it is just 1. So it's actually 1.00, and then there's some other decimals down here that are larger than zeros, but to 3 sig figs, we can just take it as 1.00. So that's good. The amount then that the light refracts is determined by what we will call the law of refraction. So remember, we have the law of reflection for mirrors. Here we have the law of refraction. To define how much the light bends, we are going to do something very similar that we did with mirrors. We're going to define a normal line. So, normal line perpendicular to our interface. I'm going to draw in a normal line here, perpendicular to the interface, that connects to the interface right at the point where the ray goes from one medium to the other. We'll now define angles for each ray, our incident ray, which I'll just refer to as the ray in medium 1, and our refracted ray, which is the ray in medium 2. And I'll define these as the angle from the ray in medium 1 to the normal line. I'll call this theta sub 1. And the angle between the normal line and the refracted ray, I'll call this angle theta 2. The law of refraction, which is also referred to as Snell's law, is not too much more difficult than the law of reflection, but it is a little bit more difficult. And that is n1 sine theta 1 is equal to n2 sine theta 2. Very good. Let's stick some numbers in here. Let's imagine that we have an air-water interface. So this would be like, just like on a smooth lake or something like that, or water in a sink, or even in a glass or something like that. And let's imagine that we have an incoming ray in the air with an angle, well, theta 1, of 45 degrees. Let's see if we can figure out what is our refracted angle in the water. Well, we need to know what the indices is the plural of index. We need to know the indices of refraction. First of all, what's the index for air? I'll call this n sub A. What's that? What's the index of refraction for air? 1.00. And then the index for water, you do not need to remember this, although we will see it very often. Water is a very common element, or common, I shouldn't say element, common material, and I'll use this often as an example. The index for water is 1.33. Let's figure out what the refracted angle is, theta sub W, say. Well, using the law of refraction, we have that NA 1.00 times sine theta A, which is 45 degrees, is equal to NW 1.33 sine theta W. So solving for sine theta W, we have sine theta W equals 1 times sine 45 degrees divided by 1.33. We divide that out and we find that that is equal to 0.532. 0.532. Taking the inverse sine, so we'll have that theta W is equal to the inverse sine of 0.532. And we find that theta W is equal to 32.1 degrees. 32.1 degrees. Very good. I want us to notice a few things about this. First, 32.1 degrees, that is less than 45 degrees. In other words, the refracted ray is closer to the normal line than the incident ray. In other words, this ray is going to be refracted down like that. Very similar to what we saw with the plastic in our demonstration. So we've got a ray that is going to refract down that way with a smaller angle. Let's come back to the law of refraction just for a second. We've got n1 sine theta 1 equals n2 sine theta 2. If n2 is larger than n1, in order for the product on this side to be the same as the product of this side, sine theta 2 must be less than sine theta 1. Let me just give you a very simple example with numbers. This is the way I always think of things, very, very simply. If we have, let's say, 2 times 6, 2 times 6, and don't worry about significant figures just for a minute. 2 times 6 equals what? Well, 3 times what? What do I have to multiply by 3 to get the same number as 2 times 6? Well, 4. 2 times 6 is 12. 3 times 4 is 12. Notice, if I increase the 2 and make it into a 3, I have to decrease the 6 and make it into a 4 in order for the product to be the same. If I increase one side, I have to decrease the other for the product to be the same. So what do we get out of this? Well, if we increase n1, we go from 1 to 1.33, we must decrease the theta. Sine theta, to decrease sine theta means to decrease theta. So if we decrease sine theta, we have to decrease theta. So that theta 2, theta in the water, must be less than the theta in the air. Well, what does this tell us in general? In general, this means if we go from a smaller index to a larger index, the ray gets bent toward the perpendicular, toward the normal line. We go from a smaller index to a larger, the ray gets bent toward the normal line. But again, if we go from a point A to a point B, we could also go from point B to point A. There's no reason why I couldn't put 1.33 and 32.1 degrees on this side and figure out what theta 2 had to be on this side, which would be 45 degrees. On the other hand, then, if we go, we could just imagine turning these rays around and going the other way. If we go this way and this way, then if we go from a larger index to a smaller index, the ray is bent away from the normal line. Very interesting. Very general rule of thumb. Let's keep that in mind. When we go from a smaller index to a larger index, the ray is bent toward the normal. If we go from a larger index to a smaller index, the ray is bent away from the normal. Very, very good. Let me give you some more numbers and let's see if you can figure this one out.